Welcome back to Industrial Automation course, Lecture 13, Sequencer and Shift Register Instructions. Today's topics are as follows: mechanical sequencers, sequencer instructions, sequencer programs, event-driven and time-driven sequencers, bit shift registers, word shift operations. Mechanical sequencers. Mechanical sequencers are often referred to as drum switches, rotary switches, stepper switches, or cam switches. So these are different names for mechanical sequencers. So here you could see a symbol. We have a bunch of switches or different type of switches, yes, limit switches or any other types. And there is a shaft that rotates and basically opens and closes these switches with the specific sequence. Sequencers are used to control machinery that has a repetitive cycle of operation. Okay, so this one basically shaft rotates, goes through the cycle and opens and closes switches. Here you could see a switch assembly, okay, inside a bunch of cam followers basically on cams basically are installed on the shaft, and this is an enclosure of the switch. Okay, so all those switches are inside, and this is the main shaft. A cam operated sequencer switch uses an electric motor to drive the cams. So here we have these cams installed on the motor, and you see there is an offset between these cams, and when they come to the contact with the switches, they open the contact, and when it basically reaches to the slot here, the switch will be closed. Okay. As the cams rotate, load devices connected to the contacts can change from an on to an off state, from an off to an on state, or remain at the same state. Okay, so very similar also to the retentive time delay switches. Yes, so that's why they could also retain the state of one switch if the motor stops. But basically the point is that we could turn switches on and off on a specific sequence time-wise. Mechanical drum operated sequencer switch, same basically, I could say this very similar structure, same structure as the cam one, and you see there is a drum connected to the shaft of the motor, and on each section we have some pegs. Okay, so they could be pegs or they could be just a plain one, okay, without any pegs. And when these pegs come into contact with these switches, then the switch will be on or will be activated, and when the switch passes these pegs and are in the basically the plain area, the switch will go to the basically off state. So you see how it operates. We have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 switches. Okay, and here we have 4 steps. So it means that in each step we have one combination of on and off, zeros and ones. Okay, and when we move to another step, then that combination changes. Each location where there was a peg is represented by a 1 or on, and the positions where there were no pegs are each represented by a 0 or off. A washing machine is an example of the use of a limited sequencer, as are dryers and similar time clock control devices. So washing machine or dryers are basically a sequencer. We choose a program, and when we choose a program, basically we are selecting a specific sequence, and the machine goes through that sequence, no matter what, okay? Specifically the old ones, not the new ones or more advanced ones. They just go through the cycle. That's it. So here you see the motor and the contacts, and basically it's same as those drum motors. Okay. So let's see what is happening here for this case of washing machine. We have 1, 2, 3, 4, and 5 switches here. And you see that each switch take care of one stage, for example, drain pump, or fill valve, or timer motor, or circulating motor, or heater. And we need to go through this cycle of washing, yes? For going through the cycle, we need to choose a specific combination of these switches, and some of them should be on, the other one should be off. So you see that on each step we have one specific combination, then goes to the next stage. For example, it goes to, I don't know, circulating motor for drying, and we need another combination. Sequencer instructions. Program sequencers perform on or off patterns similar to that of a drum switch. So here for Allen Bradley PLCs, for RS Logic, basically we have here sequencers SQC, SQL, and SQO. We'll discuss these specific instructions one by one. And here we have a sequencer file. So you see on each positions, okay, or on each steps, we have specific combination. On the first one, 0, which is basically the initial position, all switches are off. On the second one, the first 2 are off, then we have 2 on, and so on and so forth, okay? And basically what is the main task of sequencer is to go through these positions one by one, okay? So we'll discuss this, how we could change the position later. Is it the time based or event based? We'll go through that. But for now, we want to understand this table is basically that drum, okay, which is rolled. That if we basically roll this sequencer file around the drum, then we will have that drum switch. So the only difference is that on these 1 positions, we need to install a peg, okay? And those 0 are those simple or plain ones without any pegs. Okay, SQO sequencer output uses a file to control various output devices. So far we mostly discuss SQO, the previous slide, that sequencer file or DROM switch. What DROM switch basically does is similar to the SQO. We have SQL, sequencer load. We'll discuss this in the related slide when it comes to that section. And this video will discuss that. Captures reference conditions by manually stepping the machine through its operating sequences. So if I want to say briefly what it does, SQL, we could create that sequence file. Okay, so we are not reading from any sequence file, we are creating that sequence file manually. SQC sequencer compare bits from an input source file to corresponding bits from data words in a sequence file. And so basically SQC, we are trying to find a specific combination of switches from our sequence file. So we want to see if that specific combination exists in our sequence file or not. Okay, so it's kind of like searching through a lookup table or a sequence file table. Okay, so we will discuss SQL, SQC later, but first we go to SQO because it's the most common one, plus is the most intuitive one. We already discussed mechanical devices similar to the SQO, and we want to see how we could use SQO in PLC programming. Okay, so here we have SQO instruction. You see we have file, mask, destination, control, length, position. We have enable bit and done bit also. And we see what are these ones. Yes, what is file? File, starting address for the sequencer file. Okay, so this is the starting address that points to the sequencer file. Or sequencer file is there, is in this address. We could find it by the file address here. Okay, mask, bit pattern through which data are moved. So mask is kind of like a filter that or a file should go through the mask. Okay, so sometimes we don't have access to the sequencer file, we cannot easily change it, but we could easily change our mask. Okay, we can easily change the mask. We'll discuss the mask. We have a couple of examples coming. We see what is mask exactly. Okay, destination, the address of the output word or file. So once we are in a specific position on the file, then we are reading that line. Okay, that combination of those zeros and ones for the switches, and then we just write that in the destination address because this is our output. Okay, destination is output address. Control contains the enable bit, down bit, and error bit parameters. Length, the number of steps of the sequencer file starting at position 1. Position 0 is the start up position. The actual file length will be 1 plus the file length entered in the instruction. Okay, so how many positions basically we have? When you have 4 positions, then the length will be 4. And position, the word location or step in the sequencer file from which the instruction moves data. Okay, so this positions indicates where we are in our file. on each step. We are step 1, step 2, step 3 or 4. Yes. So if we look at the position number, we know on which step or position we are. So we could navigate through the file and understand what's happening in our program. To program a sequencer, binary information is first entered into the sequencer file made up of a series of consecutive memory words. So these are basically words. The start is one word, 1, 2, 3, 4, 5, 6 bits. So this one is one word. This step 1 is one word. So you see that here, what is the length? Length is 5 here. 1, 2, 3, 4, 5 possible positions we have. And basically, these are the binary numbers we are putting into the sequence file. Okay, so we have a bunch of ones and zeros. The sequencer bit file contains bits representing the output action required for each step of the sequence. So on step 1, let's say switch 1 is on, second switch is off, third off, fourth off, fifth off, and sixth is on. And then we move to the step 2, and now we have different combinations of on and off for switches. As the sequencer advances through the steps, binary information is transferred from the sequencer file to the output word. So basically, we are just copying and pasting the word on each step to the output word. Okay. Sequencer used to control traffic in 2 directions. You see that it's pretty much nicer to use sequencer to write a PLC program for traffic lights on 2 directions. We have 2 red lights on north-south and east-west, and on each step we see a different combination of lights, okay, red, green, and yellow. And how many outputs we have? We have basically 6 outputs. Okay, so here you see that we have 6 outputs, 0, 1, 2, 3, 4, 5. The rest of the sequencer file is not used. We are only using the first 6 bits. And we have 4 steps. The first position is the start position, and then we have step 1, step 2, step 3, and step 4. You see that step 1, basically the output 0 is on, and output 5 is on, the rest are 0. Okay, and same for the step 2, step 3, and step 4. Okay, now we have this sequencer file. What we need to do only to move from one position to the other one based on some conditions, yes, and we see how we could move from these positions. Sequencer program used to control traffic light. So we already created the sequencer file, and now we have a mask, okay, and a destination. So what is the mask here? Again, mask is basically easy way to turn on and off some outputs without touching or changing the sequencer file. So once all of the bits are 1 on the mask, then everything goes through. So here for the start, 0 goes through, 0 goes through, yes, everything goes through. So easy, yes. So this one is an easy filter that passes everything through. For the second step, once we have this specific mask, then again, what would be the output destination? Here, the first bit will be 1, 0, 0, 0, 0, and 1. So I'm talking about step 1. Okay. But for the step 1, if I turn the first bit to 0, then the output here will be 0. Okay, so it doesn't pass 1, and the output will stay 0. So this is mask, and usually we show mask in hexadecimal format instead of binary format. So binary format is easy to understand. You have 1, 1, 1, 1, 1. Yes, so it's easy in the binary format. So you see, B means binary, H means hexadecimal. Okay, so H is not part of the numbering. It just shows the numbering format. Okay, so the numbering format is hexadecimal. For the second one here is binary. What we need to do, we need to convert it to the hexadecimal, because in many PLCs they use the hexadecimal format, and that will be a 3F. Okay, so here we have the mask 3F, and the file. What is the file? This is the start of the file. We said that it refers to the first word of the file, which is a B30. Okay. What is the destination? Destination is O2. Okay, so this is our destination O2, which could be O20, O21, O22, O23, O24, O25. Control is R60. Those enable bits, down bits. If we want to access to those, we could access it through this address. Length is 4. We have 4 steps, and we are at the position 1. Okay. The sequencer output instruction requires preceding logic on the rung where it is located. Okay, so this is a preceding logic here. You have a SKU. Okay, and this is just a push bottom. Yes, so once the push bottom is pressed and is true, then basically we go, this sequencer will be energized. So here we have our sequencer file and the destination, or these red lights. When this logic goes from false to true, it triggers the sequencer to perform its functions. Okay. So for example, for some passenger lights, it only could be triggered by a push button. The passenger should press that button. Otherwise, it's off completely. So it's quite similar. But for many traffic lights, they are automatic. Yes, so we don't have a push button. Sequencer programs. A sequencer program can be event-driven or time-driven. An event-driven sequencer operates similarly to a mechanical stepper switch that increments by 1 step for each pulse applied to it. Okay, so we need to basically, for each event, we need to trigger it and move it to the next sequence. Okay. Otherwise, it doesn't change the status of the sequencer. Sequencer will stay as it is. We need to each time trigger it to move to the next word in the sequencer file. A time-driven sequencer operates similarly to a mechanical drum switch that increments automatically after a preset time period. Okay, so let's say we have a constant speed on the drum, and the distances between the peaks could give us that time-driven sequencer. So there is basically a time delay between each sequence, and they are different, could be equal, but it works on a clock, yes? So it works based on a clock. It's not an event-based one. And I could say that traffic light on two directions are one example of time-driven sequencers. A sequencer chart is a table that lists the sequence of operation of the outputs controlled by the sequencer instruction. So I could say it's very similar to the sequence file that we already discussed, just a different style. This one is a matrix style chart, and this is pretty simple, basically sequencer file words. For example, the first word here, the first one and the last one, outputs. I'm talking about outputs. They are on, and the rest are off. So time-driven sequencer with limited steps that are not all the same. For example, for the traffic light, the first traffic light north-south is red, and for 25 seconds, the east-west traffic light is green, and in the other 5 seconds, yellow. Then it changes to red light, and the first one north-south goes to green and yellow. So you see that we have specific time intervals, yes? This sequencer program is used for automatic traffic light control at the four-way instruction, okay? Traffic light program. So here you see how we are programming a traffic light. So first we have that a sequence file. We already created that sequence file. Please refer to the previous slides to see how that sequence file was created. Mask, you see that is FF in hexadecimal. It means that we have all ones and it passes everything through. We don't have a specific filtering, basically. Destination is O2, is the address of these lights. North, south, and east, west lights. Control address, the lengths, we had 4 steps. And at the beginning, we are at the position 0 or at the initial one. Okay. Now, we have basically here another SQO. Okay, and you see the difference between this SQO and the other one is the destination. And destination is a preset time value of the timer. Okay, so we are changing the preset time value of the timer. And what is the timer here? The timer at the beginning has 25-second preset time value. Okay, once the down bit of the timer is true, then it will trigger this sequence file, this sequencer output file, and the second one. And by triggering, we are first changing the preset time value of the timer. So we are on each trigger, we are moving through the sequence table. Okay, so we are changing the sequence. We are changing the preset time value of the timer by the second sequencer, and the first sequencer basically rules the lights on the north, south, and the east, west. So you see that we need to have a different sequencer file for the second output based on the previous slides that shows what is the time interval between each lights. Okay, so these lights, they have specific time intervals, and we need to create that sequencer file. Sequencer with constant time interval. This is one example here. We have 16 outputs. You see, these are our outputs. This is our sequencer file, and we have 8 steps. See that we have 8 steps here, and on each step we have a specific combination for outputs on or off. So here, basically, when the switch is just to start the program, okay, so the switch should be on, and once the down bit of the timer, okay, once the down bit of the timer is false, then this one becomes true, and it triggers the sorry, this is on the second one. Once the down bit of the timer is true, then it triggers the sequencer. You see again the mask, we have all F, so it's just all ones. It passes everything through. We don't have any specific mask here. We don't have any filtering. And whatever we are reading from the sequence file will go through and will be pasted on the destination file. And here we have a fixed preset time value for the on delay timer. Okay? So we are not changing the preset time value for the on delay timer based on a sequencer file as we had in the previous example for traffic lights. Event-driven sequencer output program. Okay, so here we have 2 switches, and based on the events, based on the status of the machine, these switches could go on and off. And then by these switches S1 and S2, we could move through this lookup table or sequence file and changing the status of our outputs. Okay, here see the mask. We have a special mask here. These are off, so these ones will stay off always, because you see here we haven't used these specific outputs. That's why we have mask 0. Okay, the rest are 1, and by S1 and S2 we could move through the table. The sequencer input SQI instruction allows input data to be compared for equality against data stored in the sequencer file. Okay, so this is another instruction. So far, we've been discussing SQO. So we discussed SQO. Now we are moving to another instruction, which is SQI. So let's say we have a specific sequencer file at this address. Okay. And we have inputs. Okay, so these are inputs. So these inputs, this is different from SQO, yes? On SQO, we had input to trigger or sequencer and moving through the table. But here, we have inputs equal to the number of columns in our sequence file. Okay, so here we have how many inputs? 1, 2, 3, 4 multiplied by 4, we have 16 inputs. And here in our sequencer file also we have 16 columns. Okay, so let's say at this specific time we have this combination of switches. Okay, so the first one and the second one and third one and fourth one are 0, okay, or off. The fifth one is on, and so on and so forth. So we could continue to the end. Okay, we continue to the end. And this is our sequencer file. This is our sequencer file. And if the input matches to one of the rows or the words in the sequencer file, the output will be true. Okay, so the pilot light basically goes on if the input combinations matches to one of the combinations in the sequencer file. Okay, so basically we are searching through the sequencer file and see if we have that specific combination of inputs in the sequencer file. If we have it, the output will be on. When the SQI is paired with an SQO instruction with identify control addresses, the position is incremented by the SQO instruction for both. Okay, so this is SQI and SQO paired together. Okay, and they have a different file number. They have a different sequence file. They could have different mask. You see the source here is input, but here we don't have source, we have destination. Okay, we have length and position, and here once, let's say, the input matches to one of the words in the sequencer file in the SQI, the output will be true and triggers a SQO, and we could move to the second word or step in the SQO. This type of programming technique is used to monitor and control, respectively, a sequential operation. So we are monitoring by SQI and controlling by SQO. The SLC500 sequencer compare, or SQC, instructions are similar to the SQI instruction. So far we discussed SQO and we explained what is SQI. In SLC500, SQC is very similar to SQI. Differences between the two include the SQC instruction is an output rather than input instruction. The SQC instruction increments the position parameter. The SQC instruction has an additional status bit, the found bit or FD, when the source pattern matches the sequencer file word FD is set to 1. Okay, so slightly different, but almost the same for the purpose of these slides. It's good to know that also we have SQI and we could use it in SLC or any other type of PSC program. Sequencer compare SQC instruction program. Here we have one example. We have 4 switches here. Okay, we are not using other inputs. Okay, except the first input. Okay, first input is also used to trigger the SQO. Okay, so let's say at this time we have this specific combination of 0, 0, 1, and 1, and you see it matches to one of the rows or words in our sequencer file. Okay, so it matches here. So you see the found bit, because it matches to one of these, so the found bit is true and the pilot light goes on. The sequencer load or SQL instruction is used to read the PLC input module and store the input data in the sequencer file. So by SQL, we are creating the sequencer file. We are not reading a sequencer file. We are not comparing our inputs to the raws and words in the sequencer file. We are creating a sequencer file. For example, a robot may be jogged manually through its sequence of operation with its input device read at each step. Okay, so let's say the operator wants to jog the robot manually, and on each step we want to read the data, and we want to create the sequence file. Later, the robot could go through that sequence file and do the operation automatically. Sequencer load SQL instruction program. So here we are using SQL, and the inputs are basically these 16 switches here. At this time, we have this specific combination, or at this step, the first four are zeros, the fifth one is 1, the sixth is 0, and so on and so forth to the end. Okay, so we have this specific binary combination for the switches. And what we could do with this SQL, we could now store this combination in the sequence file. So here at the position tree, we are writing position tree, we are creating position tree. The length is 5, the address is known, the source is known, yes? So at this time, at this step, we are at the step tree, and we are creating this line, and we could move to the next position, change the combination of inputs, and again, store them, save them. Here it just shows the limit switch, and these are limit switches. Let's say we have those 16 of those limit switches. Okay. Bit shift registers. So we are moving to another topic. It's different from sequencers. A bit shift register is a register that allows the shifting of bits through a single register or group of registers. Okay, so we have 1, 2, 3, 4, 5, 6, 7 bits here. And the bit shift register shift bits serially from bit to bit through an array in an ordinary fashion. Okay. A shift register can be used to simulate the movement or track the flow of parts and information. Okay, so let's say we have these parts, we want to track the flow of these parts. Okay, let's see in examples. Basic concept of shift register. This is the initial position of bits. And if we shift it to the right, you see that this one goes to this position, okay? One here, this one basically come here. The second bit comes here, third, fourth, yes. But what happens to the last one? Yes, last one will move to the beginning. Okay, so the last one move to the beginning. Again, another pulse and another move, and you see that what's happening, this 0 coming to the first, and everything moved to the right. shift pulse or clock causes each bit in the shift register to move one position to the right. The data 1 or 0 can represent the presence or absence of parts. Okay. Type of shift registers. Bit shift right register. Okay. It's the first one. And you see how the bits are moving to the right. The last one, of course, comes to the beginning. This is the most significant bit address, this one, because it's changing the position, and this is our focus here. Bit shift left or BSL register, see that the bits are moving to the left and the first one goes to the last. This is the cycle. The least significant bit address, it's at the end. Wraparound or circulating shift register, both of them are wrapping around orbits or circulating orbits, either to the right or to the left. Okay, so we have bit shift right and bit shift left, BSR and BSL. When working with the bit shift register, you identify each bit by its position in the register. For example, there may be a specific type of package that you want to track, and you only move a 1 into the register when that type comes to our system. On the discharge side, you may have an arm that pushes your packages off the belt when the shift register shows it is in the proper location, but ignores other packages on the belt. Okay, so let's say we have these packages coming, and one position could be, let's say, 0, the other one is field and is 1. Okay, empty position is 0 and field 1 are 1. How do we register that by the camera? Camera knows, yes? It moves forward. Okay, it moves forward, and then we have an arm that the arm based on 1 and 0 select to reject from the belt or change the direction on the belt or not. And once they are moving forward, we need to also shift these bits forward. Bit shift left instruction. BSL loads a bit of data into a bit array, shifts the pattern of data through the array to the left, and unloads the last bit of data in the array. So here we have 20 bits. We have 20 bits. This is the least significant one, and this is the most significant one. This one at the end will disappear. Okay, so let's say this is the last material going off the belt, and the new material will be replaced. Okay, so this one by the camera says if we have a part or we don't have a part, or for example, if we have a healthy part or infected part, yes? So it could be either 0 and 1, and we need to shift these bits forward. BSR loads a bit of data into the bit array, shifts the pattern of data through the array to the right, and unloads the last bit of data in the array. So this is the last bit and this is the first bit. Okay, so we are unloading this bit and loading this bit. The BSL and BSR instructions have the same operands. File addresses of the bit array you want to manipulate. Control R data table type used to control the instruction down bit, enable bit. Bit addresses of the source bit. Okay, so this is let's say that input from the camera. Yes, length indicates the number of bits to be shifted or the file length in bits. The status bits of the control board are enable bit is set to 1 when the instruction is true. Down bit, the down bit is set to 1 when the instruction has shifted all bits in the file one position. Error bit, the error bit is set to 1 when the instruction has detected an error, which can happen when a negative number is entered in the length. Okay, so it should be either 0 or 1. So any other numbers are not accepted or acceptable. Unload bit, it is the bit location into which the status from the last bit in the file shifts. Bit shift left instruction program. This is just one example similar to the other one. We are unloading from this one will be unloaded, and this one at the beginning will be loaded. You see that we are shifting to the left, and this is the address of a file. Okay, so this is the address of the file, and the bit address is I11, this sensor here. Okay, so once we unloaded, we will load with the status of the sensor. When we are shifting based on the limit switch status. Okay, so when the limit switch goes from off to on, we shift to the left, we read the sensor and load it to the first one, and we'll unload the last one. Bit shift right PSR instruction program, very similar to the previous one. We're just moving to the right. Bit PSL instruction program with wraparound operation. We have a clock. This is a clock with 3-second reset time value, and basically each 3 seconds we are shifting our bit register forward. Okay, and we are turning on and off these pilot lights based on the bits in the bit register. So the first, second, and the third bits. So we could change the status of these pilot lights based on what we have in the bit register. Shift registers are used in material handling processes where some form of binary information must be synchronized with the moving part on a conveyor. Okay, this is our camera that do the registering. The sensor that drives the data line on the shift register detects the presence or absence of a cartoon. A logic 1 sensor condition state can indicate the presence of a cartoon, and 0 the absence. Okay, so as these cartoons are, or these containers here, let's say these are juice containers, are moving on the build, we are shifting or shift register, okay, based on the input of the sensor. Spray painting operation controlled by a shift left register. Here we have a belt. You see these hangers, and let's say these are, I don't know, part of a chair. Okay, yeah, I'm not sure, a plate, yes. And these plates are hanged on these hangers and are moving from one stage to another on this conveyor belt. So the first limit switch shows that one part is already entered. On the first step, we have undercoat spray gun. Inside the oven, we have 2 stages. On the 5th stage, we have top coat spray gun. Inside the oven, 2. Also, we have 2 stages. And finally, the last limit switch shows that if the part exits from these sequences. Okay, so we have a reset and pilot light out inputs and outputs, and finally we have a storage here. Okay, so for each station we have one address. It could be either 0 or 1, and 0 shows that the part exists or it doesn't exist. So see what's happening here. The first limit switch register the existence of a part, the presence of a part, okay? And then when when the conveyor moves forward, we need to shift the part forward, and we need to shift the bit of the part forward. So when it basically reaches to the state, from here. So when it reaches to the stage 2, which is the spray gun, knows that there is a part and starts spraying. When it reaches to stage 2 and 3, we know that it's inside the oven and oven operates, yes, and so on and so forth, yes. And finally, when the last limit switch confirms that the part is at the exit, then we could also unload that bit from the register. The status bits of the control word are: enable bit is set to 1 when the instruction is true. The down bit is set to 1 when the instruction position equals the length. An empty bit, EM, the empty bit is set to 1 when all the data have been unloaded from the FIFO file. So first in, first out file. Okay, so we are moving to 2 different type of instructions, FIFO and LIFO. The first one is the first in, first out. The second one is the last in, first out. So they are mostly used in stacking and storages. They could have also other applications. So in a horizontal storage area, we have first in and the first out. Okay, so here we have one input, and the other one at the end will go outside. Okay. Here we have last in and the first out. This is used for the vertical storage area, and the most recent one basically goes outside. The parameters required for the FIFO unload instructions are: FIFO, address of the file in which the data are entered, destination address to which the FFU unloads data, control a three-word element that consists of the status word, the links, position. When it's paired with the FFL, the control addresses are the same: links, file links in words, position, next location from which data are unloaded. How data are indexed in and out of a FIFO file. So here we have FFL for loading. So both of them are FIFO. One is loading, the other one is unloading. It's very similar to the shift register, and FFL that loads data when it has something in the source will load it to the beginning, and the unload one is loading from the last one. Okay, so this is the destination and this is the source coming to the beginning, and the last one will go to the destination. So data index forward, the starting address of the file, one word with each false to true transition of the FFU. And you see this is our bit register here, 0, 0, 11, so on and so forth. You see that source is F10, sorry, N710. Okay, so this is the source, and destination is N711. And the address of FIFO is, for both of them, is 712. Okay, so we know that what is the address and what is the links. So based on the address and the links, we could find in the memory, the links of the shift register or the shift register bits. We know this is the beginning and this is the last, and we are reading from the source, which is this at this address, load it here and unload it from here to this address. The first in, first out instructions often used for inventory control. Each part is assigned a unique code which is loaded into a FIFO stack, and the parts are removed in the order prescribed by the stack. Okay, so they have a barcode, they have a number, and that will be loaded into the FIFO stack. This type of control ensures that the oldest part in the inventory is used first, as the first part enter is the first part moved. Okay, so exactly as we could see in the conveyor belt, the first one come and this one must be removed first. Okay, we cannot remove the middle one, so it goes to the end and then will be removed. Okay, so very similar to the shift register. The last in, first out instruction inverts the order of data it receives by outputting the last data received first and the first data received last. Okay, we already explained it in the vertical inventory example how it works. And in terms of the addresses, destination, and source is very similar. You see that this is for LFL loading and unloading. You have LIFO type, and this is where we could find LFL and LFU instructions, both in pair. For FFL and FFU also in RS Logics and Allen Bradley type of PLCs, we could find it in the program. LIFO instruction per program, we have loading and unloading. you see that LIFO address for both should be same, so they are the same. We know that is 73, so it starts from here, yes. We know the length is 64, so it comes down to 64. So we know the length. So here, what's happening here, we have for the load, we have a source. So it's reading from this address in the memory is 71, and the destination is 72. And you see that basically whatever is coming to the stack goes to the destination, okay? Very similar to the vertical storage, okay? But if you remember, for first in, first out, or FIFO, we were loading to the beginning and unloading from the end. Okay, so this is the difference here. The LIFO stack operates similarly to that of the FIFO stack, except that the last word in the LIFO stack is the first word that is unloaded from the